Section 11.2 is a pretty tough section here, guys. We're getting into an important concept here in geometry called area of regular polygons. And I decided to break this section up into two different parts right here. The first thing we're going to do is what I'm just calling nice ones here. And when we get to 11.2b, those are going to be some of the tougher polygons that are out there. But first, I want to kind of explain to you guys where the formula is going to come from that we're going to be using on all of these problems here. So I thought it would probably be good to refresh our memory from our chapter a while ago on polygons to remember what a regular polygon is. And that word regular means that all of the sides and all of the angles within a polygon have to be congruent. So squares would be an example of regular polygons, equilateral triangles, and there's all sorts of other ones out there. This one that I've drawn right here, guys, is a regular hexagon, but we want to start walking through where this formula comes from, so we got to introduce a little bit of vocabulary here. Now, the first thing I'm going to try to do within this hexagon here is locate what we call the center of our regular polygon, and as you might guess, the center is going to be located right there in the middle, so that point right there is going to be our center. Then from there, we're going to introduce two important things. So I guess let me go ahead and write the word center right there. The first thing we're going to discuss then is something called the radius of a regular polygon. And a radius, which is what I have just drawn right there, that's a word that we usually reserve for a circle. But a radius in a regular polygon is a segment that goes from the center to one of the vertices of the original regular polygon there. So that's our radius. And then this other segment we're going to be talking about today is a brand new word that I'm fairly certain you guys have never heard of before. If I were to drop an altitude from my center right down to the midpoint of one of the sides, that is a goofy word here, guys, called an apothem or apothem. I've heard geometry teachers pronounce that both ways there. Either one of them would be fine. I generally say apothem. And the apothem then is the segment that goes from the center of your regular polygon to the midpoint of any one of the sides. So to show that that's a midpoint, I'm going to put a double tick mark here and a double tick mark right here. And also, that always ends up being perpendicular to that side that you drew it to. So that word apothem is really important here in this section, guys, and we want to make sure that we have that pretty well written down in our notes because we're going to be referencing that a lot. Okay, so what you'll notice right there, guys, is that when we drew an apothem and a radius, we formed, let me switch colors here, we formed a right triangle here kind of in the middle of that figure. And coming up with the area of that right triangle there in blue is really going to be the key to coming up with the area of the entire regular polygon. So let's go over here to the right, guys. I kind of have a list of things going on here. We're going to introduce some variables. Now, the first thing I want to talk about is the number of sides in your regular polygon. And we're all going to be tempted to look at this figure right here and say, oh yeah, clearly the answer is 6, but that's actually not the way we want to handle this. If we wrote down 6, that would only be specific for a hexagon. But instead, we're going to use a variable called n to represent the number of sides. We've done that in the past. So in a hexagon, n will be 6. In an octagon, n will be 8, and it will go on from there. Now the side length here, remember that if this is a regular polygon, all of the sides are going to be congruent. So we're going to say that each side length is going to have this generic variable here called s. And again, that will change from problem to problem. The apothem, that length is simply going to be called a. That makes some sense right there. And now the number of isosceles triangles. Now this gets a little bit confusing. The isosceles triangle comes from drawing two radii right next to each other. So I wouldn't do this in your notes, guys. I'm going to shade this in. What I have in red here is an isosceles triangle. Every radius within a regular polygon is going to be congruent to itself. So what I have there in red is one isosceles triangle. Well, here's a second one. Here is a third one. Here is a fourth one. I've got a fifth one here and a sixth one right here. So in this particular figure, I have 6 of those isosceles triangles. But that won't always be the case. The number of isosceles triangles is going to match the number of sides in your figure. So let me get rid of all that junk that I just put right there and say that the number of isosceles triangles is going to be the same as the number of sides, and that is going to be n. So now that we've introduced a few variables right here, let's start talking about what's going on here, guys. Okay. In this figure right here, we want to first start off with the area of that triangle. And I think I am going to go ahead now and draw that second radius here that I had just a second ago. Let me move what I did with apothem right over here, put that back, and I'll just draw an arrow from the apothem to that piece right there. That would have been smarter. Now I'm going to go ahead and shade in the other half of this triangle here as well. So this blue triangle, guys, that's what we're trying to measure right here for area of that triangle. Okay, so the formula for the area of any triangle is 1/2 times its base times its height. Now the base of that triangle right over here is exactly the same as the side length in your regular polygon. So the base of our triangle is S. And the height of that triangle is this piece right over here. Remember that base and height have to be perpendicular to each other. Okay, and the height of that is the length of our apothem. So 1/2 times S times A, where S is the length of each side and A is the length of your apothem. That's going to give you the area of that one blue triangle that we have highlighted on the bottom. So now, if we wanted to take that idea and now figure out the area of the entire regular polygon, it's just a question of how many of those blue triangles we have. And we answered that question right here. We have n of them. So the area of the entire regular polygon would be 1/2 times S times A. That's the area of one triangle. And then we would multiply that by n, which is the number of triangles that we have. And this right here, guys, is really a formula here for the area of the entire regular polygon. 1/2 times side length times apothem times the number of sides. But we can clean that formula up just a little bit here, guys, to make our lives just a little bit easier. If we were to think about the length of each side here and then the number of sides, if we were to multiply those two ideas together, that's going to get us an important idea called the perimeter of your triangle, of your figure there, guys. The number of sides times the length of each side. That would be n times S. So I can take out the S and the n, and I can replace that here with a P for perimeter. And now that I'm looking at this, I think I have one too many lines right here. Here's the formula, guys, we need for area of a regular polygon. Whoa, what was that? All right, let's try this again. That is going to be 1/2 times capital P, which is the perimeter of this figure, multiplied by A, which is your apothem. Okay, so that's the formula in the box right here that we want to make sure we have written down. Frankly, nothing else on this first page is super important for you guys to know, but we absolutely have to know this formula right here. Area, and the RP stands for regular polygon. Area of any regular polygon is 1/2 times P, which is its perimeter, and little a, which is its apothem. So coming up with that piece right there is going to be really important in these problems here. Now, I decided to give you just a couple of problems here. These are actually from the old textbook, not one that we're using anymore here. But I thought this would actually still be good stuff to go through here, because finding the apothem can get a little bit difficult, and these are some skills that we'd have to kind of master in order to be able to do that. So I just want to run through one of these here. We have a regular polygon here, and as I count my number of sides, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9 sides right here. So n is equal to 9 in this figure, guys, and the word for that, in case you've forgotten the name, is a nonagon. Okay, so we have ourselves a nonagon, and we're supposed to come up with the measures of 3 angles here, guys. Angle 1, then angle 2, and then angle 3. So let's talk about how it is that we might go about finding all of that. Angle 1, you'll notice, is right here. And this segment that I'm shading over in purple right now is a radius of that polygon, and so is this figure right over here. And if we were to count all of them, you will notice, let's see, that's 2. There are 3, 4, 5. Now be careful here, guys. The next radius is right here. 6, 7, 8, there are 9 radii within this nonagon right here, which of course matches the number of sides. And angle 1 is the measure of one of those central angles. Okay, and an angle, a central angle, is one that has its vertex right at the middle. Now, if we realize, if we were to add together all 9 of these central angles right here, that's going to make one complete circle here, guys. So what we're doing here is we're trying to find the measure of a central angle, which is what we usually call theta. We've used that variable before here. The way we always do that is we take 360 degrees and simply divide that by the number of sides that you're dealing with in each one of these problems. And in this case, n is 9. So here, this is going to be 360 divided by 9, so the measure of angle 1, 360 divided by 9, is going to be 40 degrees, and that's the first thing that they were asking us to find right there. So each one of these central angles here is 40 degrees, and I'm not going to label all of them. I'm going to go to here, and then I'm going to stop. Now, the next thing we need to do is come up with the measure of angle 2. And you'll notice that angle 2 is going to be smaller than this 40-degree central angle right here. But what's happening with angle 2? They drew the apothem right down the center of that triangle right there. So angle 2 is going to end up being half of one of those central angles. So all we're going to have to do now to find the measure of angle 2 is take your central angle, theta, which is 40 in this case, and cut it in half, and we're going to get 20 degrees for the measure of angle 2. Now, what about angle 3? If we focus on this triangle here that I'm shading, which made that very hard to read, that's a right triangle there, guys. Let me get rid of that because we knew we have another 90-degree angle right here, and we just found that angle 2 was 20 degrees. So I know that angle 2 and angle 3 have to add up to 90 as well. So the measure of angle 3 is going to be 90 minus the measure of angle 2 we just found, which is 20. So angle 3 is going to be 70 degrees. Okay, so that's not a bad skill to get used to. We're going to be doing that on a lot of these problems, guys, where we figure out the measure of a central angle, which we do by taking 360 divided by n. That's going to get us what this problem is calling angle 1, and then very often we're going to divide that by 2 to get the measure of this little angle right here. Okay, here's a second problem here, guys. This one is pretty straightforward, and I think I've given you a couple of these on the homework assignment here for 11.2a. This one's pretty straightforward. Find the area of a regular pentagon with a side length of 7.1 centimeters and an apothem of 4.9 centimeters. Now, those numbers seem pretty random, but there's actually some work that went into that. I can't just make up any numbers that I want here because in a regular pentagon, the side length and the length of the apothem are related. Now, I actually took this problem from the old book, so I'm hoping they did their homework on that. Okay, you're not going to see a ton of these, guys, but this one gives you everything you need. We're trying to find the area of a regular pentagon, so I'm going to use the formula area of a regular polygon is equal to 1/2 times capital P, which is its perimeter, times little a, which is its apothem. Step number 2, fill in what we know. Area of the regular poly is equal to 1/2, and now we need the perimeter. Well, to find perimeter, we know that in a pentagon, the number of sides is going to equal 5, and the side length here is going to be 7.1. So a couple slides ago, we wrote down here this concept right here. Perimeter is the number of sides times the length of each side. So our perimeter here is going to be 5 multiplied by 7.1, and I'm pretty sure that's going to give me 35.5, but I don't want to mess up my first problem. 5 times 7.1 gets us, 35.5 is the perimeter of this pentagon. Okay, that's not too bad. So that's what's going to go in here for perimeter, 35.5 taking the place of P. And now, the only other thing we need now is the length of the apothem, which usually is going to be something we have to work for, but right now they just spoon-fed it to us, guys. The apothem is 4.9 centimeters. So we know the perimeter, we know the apothem, we're ready to go ahead now and just put all of that into our calculator and solve this first problem. So our formula here is going to be 1/2, that's easier just to type in as a 0.5, times your perimeter, which was 35.5, times your apothem, which was 7.1. 126.1, and that's going to give us our answer here, guys, of 126.025 for this one here. 126.025. Directions didn't say where to round that, so I'll go ahead and just do everything there. Now remember, this was centimeters here for perimeter, this was centimeters here for apothem, and centimeters times centimeters is going to get us square centimeters. So you're not going to see too many problems like this, but this one was pretty straightforward. They gave you everything you needed there, and we were able just to go right to the formula. But everybody, there isn't a whole lot of fun in just doing that, so these problems get a little bit tougher. And what I've got for you now, guys, are 6 problems that I'm going to walk you through. 2 each of the 3 different types of quote-unquote nice figures here. So I wanted to start off talking about what to do with trying to find the area of a square. Now a square, this is kind of silly, it is a regular polygon where our number of sides here is equal to 4. But I say this is silly because we already know the formula for area of a square. So real quick, guys, the area of a square, well, a square is a parallelogram, is just equal to base times height. And our base right here is 10, and our height, well, since it's a square, we know that the base and height have to be congruent to each other, so the height is 10. The area of this thing is 100 square centimeters. We already know the answer, but I wanted to take the time here to show you guys that this formula we're talking about works. So I'm going to do the problem a second way here, and we better end up with the exact same answer. Let's just see if we got it. Area of a regular polygon, which a square is 1/2 times perimeter times apothem. So step 1, always start with the formula. Step 2, fill in what you know. 1/2 times, okay, perimeter of the square, the distance all the way around, that's 10, and there's 4 sides right there. So 10 times 4 is going to give us 40 centimeters for the perimeter of that square, distance all the way around. And the apothem now, we don't know the length of it because it's not even drawn yet. So let me do that. This is a habit we want to get into with most of these problems. We're going to try to locate the center of our square, and the apothem comes straight down. Really, you could draw it to any side, but just to keep things simple, we always want to draw it straight down to the bottom. There's your apothem, guys, perpendicular to that side there on the bottom or any one of those sides. Well, do we know how long that is? If the entire right side or left side of this figure is going to be 10, the apothem is going to make up half of that side length right here. So this piece would be 5, and this piece would be 5 as well. So the apothem ends up having a length of 5. And that should be everything that we need here to go ahead and multiply this out. And I think I can do this in my head, guys. Half of 40 is going to be 20, and 20 times 5 is going to be 100. That was centimeters times centimeters. So 100 square centimeters is the area of that square. Okay, that's what we're dealing with there. Squares are not all that difficult, although they can get a little bit trickier when I give you a setup like this. And in the previous problem, we were given a square where we knew the side length, so we were able to get the perimeter pretty quickly, and we were able to figure out the apothem. But in this setup right here, we've been given a radius of that square, 16 inches. So that makes this problem a little bit tougher. So let's set up our formula. Area of a regular polygon is 1/2 times perimeter times apothem. Now in step 2, I go to fill in what I know, but the issue here, guys, is I don't know the perimeter, nor do I know the apothem. We've got some work to do on this problem. So what we want to get used to, guys, is drawing the apothem and the radius if they're not already there for us. So in this figure, they gave us a radius, but I'm going to draw an apothem straight down to the bottom side here, perpendicular to that bottom piece. And what we're going to start focusing on now, and this is going to take us through the next 4 problems as well, what we're going to focus on is what kind of triangle have we just produced here? So if I walk you back to something we did a while ago, I'm going to switch to green here, guys. We were finding theta, which was the measure of a central angle, by taking 360 and dividing it by n. Now in this case, we're dealing with a square. Your number of sides here is 4. So theta, your central angle, is 360 over 4, which is 90 degrees. Now, I don't think you want to put this in your notes, guys, but what I just found is the angle between this radius and this radius right here, that is a 90-degree angle. And the same thing happens here. That's a 90-degree angle. And here, that's a 90-degree angle as well. Now this is the fourth 90-degree angle right there, but the apothem goes right down the middle of that angle and bisects it. Okay, so what we're going to do then is take that 90 and cut it in half, and that means that we're going to get a 45-degree angle right there, which, as you think about what a 45-degree angle looks like, I think that makes some sense. So we've got 45, this is 90, and this is a 45-degree angle as well. Oh, okay. So what we have in blue here, you guys, is not just any random right triangle. This is a special right triangle, a 45, 45, 90. And within that 45, 45, 90, I'm going to go to red now, we know that our hypotenuse has a length of 16 inches. So we've got to come up with A, the apothem, and this piece right here, which I always call X. So we need to remember some things about a 45, 45, 90 right triangle. And just in case you've forgotten, guys, this is going back to our trig chapter here. In a 45, 45, 90, okay, I'm hoping you guys know this, but just in case we need a little reminder, the two legs are congruent to each other. So if one of those is X, the other leg is going to be X as well, and the hypotenuse is X multiplied by the square root of 2. So to go from leg to hypotenuse, we're going to multiply by the square root of 2. But to go backwards from the hypotenuse to a leg, we're going to divide by the square root of 2. Okay, so back to where we were just a second ago, we need to try to figure out what A and X are. Well, they're going to be congruent to each other because those legs are congruent. So A, which is the same thing as X, is going to be 16, which is our hypotenuse, divided by the square root of 2. And guys, the calculator I'm using isn't going to do this as nicely as your multi-views here, but when you guys type that in, you're going to get, I am pretty sure, 8 root 2, and that's going to be the length of both A and X here. Now, that X is important because what we really need is perimeter. Okay, so how are we going to use perimeter or use X in order to figure that out? Let me make that a little bit easier to see. All right, guys, now that we know that X is 8 root 2, let me just write a couple of ideas down right here. X is 8 root 2. A side length, then, is going to be twice as long as this because there's an X right here and another X right over here. So that's going to be 2 times 8 root 2, which is going to get us 16 root 2 for the length of one side. The perimeter, then, we've got 4 sides here, and we multiply that by the length of each side, which is 16 root 2, and that's going to get us 64 times the square root of 2 for the perimeter of the entire figure. And I think that should be everything we need here, guys. So back up to step 2, filling in what we know. The area of our regular polygon is 1/2. Our perimeter, we just found right here, is 64 times the square root of 2, and the apothem, which we found way back when here, is 8 root 2. Now, once more, you guys should just go to your calculators right now, your multi-views, and type in everything that you've got right here. But I'm pretty sure when we do this, guys, we're going to end up with 512 for the answer. I'm going to try that and see if it works out. So 1/2 times the perimeter, which was 64 square root of 2. Let me hit my right arrow to get out of that. And then we're going to multiply that by our apothem, which was, help me out, 16. It was 8 times the square root of 2. And that gets us, yep, the answer I thought we were looking for, 512. Everything was in inches here, so our units are going to be square inches for the area of that regular polygon, of that square. So I wanted to do 2 examples with squares here, guys, to show you that when you draw, especially this one, when you draw the apothem and the radius, we end up with 45, 45, 90 triangles. So we might want to write that down here, guys. Right next to the word square in our notes, we should probably put 45, 45, 90. That's going to happen in every single square that we need to find the area of. Okay, so we did example A and example B. Now let's move on to something a little bit different. Now let's start talking about regular polygons that are triangles. Okay, so here's what we've got. Now again, to be regular, all three sides have to be congruent to each other, which makes this an equilateral triangle. So I'm going to draw the same thing for you guys I've been drawing before. I'm going to kind of locate the center of that triangle, which is roughly right about there. I'm going to draw a segment coming straight down to the bottom here, guys, and that's going to be our apothem. And then I'm going to draw a radius of this figure going off here to the side, and that is going to be R. So we just formed a right triangle here, and the question we should probably ask, what kind of triangle did we form? So let's do the same thing we've done a couple of times already. You find a central angle by taking 360 divided by n. Well, this should be obvious. In a triangle, n is 3. So 360 divided by 3 is going to get you 120 degrees for the measure of a central angle. So if I drew this radius and this radius right up here, that is our 120 degree central angle, and so is this. But the 120 degree angle on the bottom gets bisected by the apothem. So let's take that 120 divided by 2, 60 degrees is what we just found for that angle right there. Oh, and what do we see now? Here's 60, here's 90, this has to be a 30 degree angle right there. So every time we are dealing with triangles, equilateral triangles, guys, you are going to form a 30, 60, 90 right triangle when you draw your apothem and when you draw your radius. So we better have another refresher on that too, guys. In a 30, 60, 90, it's a scalene right triangle that looks something like this. Here's your 90 degree angle, 60 degrees, and 30 degrees. The short leg is the key. We always call that x. The hypotenuse will be twice as long as that short leg. That'll be 2x. And the long leg will be the short leg multiplied by the square root of 3. So x times the square root of 3, and that's the pattern we have to have memorized here, guys, for the side lengths in a 30, 60, 90. So back to this one, what do we know? Well, the whole bottom side here is 8 centimeters. That means that this piece right here on the bottom is going to be half of that, which is going to be 4. Okay, so we've got some work to do in order to figure out what A is, and I actually don't think we need R here, guys. Let me switch back to red here. To find A, that's the short leg in a 30, 60, 90, we would take our long leg and divide it by the square root of 3. So A is going to be 4 over the square root of 3, and when you guys put that into your calculators, I believe you're going to get something not all that pretty, 4 root 3 over 3, and I don't believe that simplifies at all, but your calculators will do that work for you. So there's the apothem that we needed. The other thing we need is the perimeter, and I think that one should be pretty easy for you guys to find. We've got 3 sides here, and each one of them is 8 centimeters long, so our perimeter is going to be 24. Okay, so here's our formula. Area of a regular polygon is 1/2 times perimeter times apothem. Step 2, let's fill in what we know. Area of a regular poly is 1/2. The perimeter we just came up with is 24. Looks like everything here is in centimeters. And the apothem we had to do some work on is this ugly number of 4 root 3 over 3 centimeters. Okay, now you guys should definitely go to your calculators right now. I'm going to try to guess what it would be here. What do I notice? The 3 and the 24, since that 3 is on the bottom, this is 24 divided by 3, which is 8. Half of 8 is going to get you a 4 right here. So then it's 4 times 4 root 3, and I think we're going to get 16 root 3 centimeters times centimeters is square centimeters, and that should be the area here, for example, 3A. So that was our first triangle problem. Drawing the apothem and a radius is going to get you a 30, 60, 90 triangle that's kind of laying down on its side, guys. It's wider than it is tall. Okay, let's do another example with that one. So here's another equilateral triangle, or a regular triangle. And in this case, it's the apothem that's been given to us right here of 5 millimeters. So the apothem was already drawn, but I am going to draw in the radius that goes right next to that. There you go, and that's R. And just like in the last problem, this is once again going to be a 30, 60, 90 triangle. Guys, there's no need to go back and redo all of this work every time. This is something hopefully you can memorize pretty quickly, that every time you're dealing with a triangle, the overall big figure, that when you draw apothem and radius, this is going to form a 30, 60, 90 every single time. Okay, what we need to do then is find this little piece right down here. That's half of a side length, which I always call X. The apothem given to us at 5 millimeters, that's our short leg. X is the long leg. So to find the long leg in a 30, 60, 90, you take the short leg, which is 5, and you multiply that by the square root of 3, and nothing is going to simplify there, guys. If you were to type that into your calculator, what's 5 times the square root of 3? It's just going to tell you the answer is 5 root 3. So that's X. S then, which is a side length, is going to be 2 times that amount right there. So 2 times the 5 root 3, and let me write that out, 2 times 5 root 3, that's going to get us 10 root 3 for the length of each side. And then the perimeter now is going to be the number of sides, which is 3, multiplied by the length of each side, which is 10 root 3, and that's going to get us 3 times 10 is 30, and the root 3, kind of like a variable, just goes along for the ride. So we know our apothem and we know our perimeter. We're ready to go to the actual formula here, guys. Area of a regular poly is 1/2 times perimeter times apothem. Let's fill in what we know. Area is 1/2 times the perimeter we just found was 30 root 3. Looks like we're dealing with millimeters here, a small little triangle here. And then the apothem, which we need right here, was given to us as 5 millimeters. Okay, and let's multiply everything out now, and let's see what simplifies. Not a ton. Half of 30 is going to end up getting you a 15 right here. Then I would multiply the 15 times the 5 to get 75, and the root 3 just tags along. Millimeters times millimeters is going to be square millimeters, and that's our area for that regular polygon. So the hard work comes from finding the perimeter and the apothem in each one of these problems. Once you get those, the actual formula itself is pretty easy to use. Okay, the final type of polygon we're going to do today are regular hexagons. Haven't done these ones yet. So what am I going to do? Just like in every problem, if it's not already done for you, locate your center, draw yourself an apothem going straight down perpendicular to the bottom side. So that is going to be A, and then draw a radius right next to that apothem. So that's the first thing we need to do on every one of these problems, guys. Make yourselves that same right triangle over and over and over again with an apothem and a radius. Now the question is, do we know what kind of triangle that is in blue? And I wouldn't want to make any assumptions here, so let's see what we can find. First thing we're going to do, let's find theta, the measure of our central angle. Remember, theta is 360 divided by n, and in a hexagon, n, our number of sides, is always going to be 6. So 360 over 6 means we're dealing with a 60-degree central angle here. I'm just going to draw one of them, just kind of at random over here. That is your 60-degree angle. Now in the blue triangle, what we're dealing with on top then, guys, right here is half of one of those central angles. So we're now going to take 60 divided by 2 and get 30 degrees for the measure of that angle. We already have a 90 from where the apothem hits the side, so this other angle there on the base must be a 60-degree angle. So, just like with equilateral triangles, with regular hexagons, we are again dealing with 30, 60, 90 right triangles here. Except this time, the 30, 60, 90 is kind of standing up. It's taller than it is wide, as opposed to what we did here, guys, where that 30, 60, 90 in the triangle was kind of laying down on its side. But all of this information right here that we just went over a few minutes ago is still going to apply to a 30, 60, 90 triangle right here. Okay, so what do we need to know here, guys? We need to come up with the length of our apothem. Let me go, I'm going to use this weird orange color right here. Okay, let's find A, the length of our apothem. So this piece right here, guys, is going to be half of that 10, so this is going to be a 5. That's the short leg. A is the long leg. So we're going to take our short leg, 5, and multiply it by the square root of 3. And that doesn't simplify at all, guys. So that's your apothem, 5 root 3. The perimeter of this figure is going to be the number of sides, which we said was 6, multiplied by the length of each side, which is 10. So our perimeter is going to be 60. Okay, so we know our perimeter, we know our apothem. This problem shouldn't be that bad. Step 1, area of a regular polygon is 1/2 times perimeter times apothem. Area then is going to equal 1/2 times a perimeter that we said was 60. Looks like everything was in inches in this problem. And the apothem, A, we came up with was 5 root 3 inches. And now let's just multiply all that out, and we should be done here. Half of 60, get rid of that weird color right there. Half of 60 is going to make 30. 30 times 5 is going to be 150, and the root 3 just tags along. Inches times inches makes square inches. So that's the area of that regular hexagon, 150 times the square root of 3. Again, the hard part is figuring out what kind of triangle you're dealing with, and in a hexagon, that's always going to be a 30, 60, 90 standing up, and then using the little information that you have, here we had the 5 for that x length there, to figure out what A was. Then we found our apothem, and we found our perimeter, and from there, actually using the formula was relatively easy. Last problem here, guys, before we wrap this one up. Once again, we've got a regular hexagon, and in this case, they've given you the apothem right here, which is 24 meters long. So the apothem's already been drawn, so let's draw a radius that goes right next to it here, guys, and that will be R, although we don't really need that piece. And once again, we have formed a 30, 60, 90 triangle standing up. So let's try to find this little piece down here, which I'm going to call X. So the way to find X, you guys, is to take, let's see, 24, the apothem is your long leg. To find X, we're having to go, let's see, in what direction here, guys? From here, the X root 3, back to this X here. And the way we do that, dividing by the square root of 3. So we're going to take 24 here, which was our apothem, and divide that by the square root of 3, and I think your calculator is going to tell you that that is 8 root 3, if I'm not mistaken. Let me think about that for a second. 24 root 3 over 3. Yeah, you're going to get 8 root 3 for X. Okay, then S, a side length here, guys, one whole side, is going to be double that amount right there. 2 times 8 root 3 is going to be a 16 root 3, and the perimeter then is the length of each side times the number of sides, which in this case is going to be 6 sides. So 6 times 16 root 3 is going to get you a big perimeter here of 96 root 3. Okay, so there's the apothem, 24 meters. Here's the perimeter. That should be everything that we need. Area of a regular poly is 1/2 times perimeter times apothem. So let's fill in what we know here, guys. 1/2 times a perimeter we just came up with of 96 root 3. Everything is in meters. This is apparently a very large hexagon, okay? And then our apothem, 24 meters. Whew, okay, we're dealing with some big numbers here, guys. So let's put them all together now. Area of a regular poly is, I think I'm going to need some calculator help here. I'm going to leave out the root 3. I'm going to do 1/2 times 96 times 24, so 0.5 times 96 times 24. Okay, that gets us 1152, so I'm going to write that down. And the only thing I didn't put in there was the root 3, and if I want my answer exact, I'll just stick on that root 3 at the end. Meters times meters is square meters. And that's our answer there to example, was that 4B? Yeah, 4B, and there we go. Okay, this is a tough section, guys. It definitely is going to take some practice to get used to. But again, the most important thing, if it's not already drawn for you, draw yourself an apothem, draw yourself a radius. And between those two sides and this piece, you have to be given one of those three. You can use that one to find the other pieces. Then you've got to figure out your perimeter, and you've got to figure out your apothem. And once you know P and A, you can go right back to this formula right over here. Okay, when we get to 11.2b, now we start dealing with triangles here that are not special right triangles, and we're going to need our calculator in order to do trig on there. Doesn't that sound like fun? But first things first, let's knock out this homework. We'll see how you guys do. Let us know when you have questions. Good luck, everybody.